We're happy to have today Nick Sheridan from the University of Edinburgh. He will explain us that quantum cohomology are in fact deformation of symplectic cohomology. And so, Nick, please, and Lina also, don't forget.
Okay. All right. Can you see that okay?
Yeah. Yes.
Okay. Okay. Thank you very much for inviting me. So I'm going to talk about this work, which is joint with Strom, Borman, and Umut, Varolgunes. And I want to make a comment about the history of the work, which is that it started as a project joint between Strom and myself, and we sort of announced a slightly different version of the results in a different version of the results around 2015 or something, and then it kind of languished, didn't get finished writing it up, and then Umut joined in 2019 and sort of pushed it to get finished, and also sort of shaped it in some quite new directions. So he deserves a lot of the credit for the project getting finished, for turning it, sort of making it more interesting than it originally was, and he deserves none of the credit for the long delay after announcement. So I want to make that clear. Okay. So let me briefly introduce the main players. So we're going to talk about quantum cohomology of a compact symplectic monotone manifold. Monotone I'll take to mean that the class of the symplectic form is equal to the first Chern class of the tangent bundle. And I'll define, so we'll take we'll choose some coefficient ring, little k, and our Novikov ring will be this capital K, which is formal Laurent series in a Novikov variable Q. And the quantum cohomology of M is just the singular cohomology of M with coefficients in this capital K, but the gradings are a bit different. Q has a non-zero degree, has degree 2. And we have the definition of the quantum cut product given by counting holomorphic spheres weighted by powers of this variable Q, this Novikov variable. So for example, this is what quantum cohomology of projective space looks like. So under mirror symmetry, we expect quantum cohomology of such a monotone symplectic manifold to correspond to the ring of functions on the singular locus of some potential, some Landau-Ginzburg model. So we have some k variety y, function w called the potential, and the mirror symmetry predicts that the quantum cohomology of M should be isomorphic to the algebra of functions on this derived singular locus, although when the singular locus of W is isolated, this is really just the ring of the derived singular locus is the same as the singular locus. So it's just the ring of functions on the singular locus of W. So for example, CPN is mirror to this well-known mirror, which we'll take to be K star to the N. Potential is Q times this familiar mirror potential to CPN, and this isomorphism between quantum cohomology and the Jacobian ring matches up. So the ring of functions on the singular locus is, I mean, in this case, it's affine. So this is just the Jacobian ring of W, which comes out to be K adjoin a single variable whose n plus first power is 1. And this is isomorphic to quantum cohomology via this map, sending the hyperplane class to Q times Z1. Okay, of course, mirror symmetry predicts more, but I just want to give you some things to hang on to on the way we're thinking about mirror symmetry for these kinds of examples that will be relevant for the talk. Okay. So rather than thinking of quantum cohomology in the way I just described it, we'll instead use the Hamiltonian Floer homology of M, which is equivalent. So for this, we need to define this, we need to introduce an auxiliary S1 family of Hamiltonian functions HT. The generators of this Floer cochain complex are orbits of H, which means loops mapping into M whose derivative at time t is the Hamiltonian vector field associated to the Hamiltonian H sub t. And the differential on the Floer cochain complex counts Floer trajectories, which means maps from a cylinder into M, satisfying Floer's equation, which is this one here. All right, so we end up with this cochain complex, which is the free K module generated by the orbits. There's a grading which I'm not explaining. And the differential, the matrix coefficients of the differential count these Floer trajectories. And this defines a differential, and its cohomology is the Floer cohomology of M, which we write this way. And Floer proved that this is independent of H, and in fact, isomorphic to the quantum cohomology of M. You can say this is because the Floer cohomology localizes at the constant loops somehow. And this result of Punikin, Solomon, Schwarz shows that this isomorphism intertwines the pair of Pant's product on Floer cohomology with the quantum cup product, which I just described on quantum cohomology.
Can I just quickly clarify the flow trajectory?
Yes.
That when you do the partial derivative with U has the value inside of M, that's a symplectic manifold. So what do you mean by that? Are you taking a value inside of a tangent space, or?
Yes. This equation is it's an equality of tangent vectors in the tangent space to M.
Okay. Thank you.
Okay. The other player in our story is symplectic cohomology. So this is an invariant of a Liouville domain. Oops, sorry. So a Liouville domain is an exact symplectic manifold. So it comes equipped with a primitive theta for the symplectic form. And given theta, you can define an associated vector field Z by this equation. This Z is called the Liouville vector field. And there's a sort of structure theorem, you could say, for these Liouville domains. You can sort of break them up into a set called the skeleton S, which is the limit set of the negative of the flow of the reverse flow of this Liouville vector field. And everything else in this Liouville domain looks like part of a symplectization of a contact manifold. So you've got a skeleton bit down the bottom, and then you've got something that looks like contact manifold cross R with its standard symplectic form. And this R coordinate, well, we'll denote by rho. So that's a function that maps to non-negative reals with the skeleton mapping to 0. Okay, so we
Sorry to interrupt you. Actually, your software has the pointer, so you can point, so we can see where you are talking, which part you are talking.
Yeah.
Yeah, you can use that one, so that
This
will help
one?
the audience. Yes, try it.
Can you see this? So you can see this now. Only if I draw, right?
I don't.
Right. Yeah, so yeah, I'm sorry, I don't know how to make you able to see my my cursor only when I draw. But okay, I don't know, this function, I mean, this is the function rho here. It's a map to the non-negative reals. And the skeleton S gets sent down here to 0. And that's why I drew 0 blue. Okay, so we can define this symplectic cochain complex of X by taking exactly the same definition that I showed for Hamiltonian flow homology in the previous slide, but for a specific class of Hamiltonians H, which are somehow adapted to deal with the non-compactness of X. So these Hamiltonians should be obtained by taking a function of rho. Okay, so H is a function of rho where the graph of this little h looks like this here. So basically it's a function which is small in the interior of sort of in, you know, near the skeleton. And then as you get further and further out, it goes to positive infinity. And then we take this Hamiltonian flow homology associated to this in the same way I said on the previous slide. And this is by definition the symplectic cohomology of X. And this symplectic cohomology also fits into mirror symmetry. Typically, in many cases, the mirror to X, a Liouville domain like this. So an affine variety carries a canonical up to deformation structure of a Liouville domain. So this is the kind of thing that you can define this symplectic cohomology for. So typically the mirror to X may be some K variety Y, and mirror symmetry predicts that the symplectic cohomology of X should be isomorphic to this tangential cohomology of Y.
Sorry, Nick, your mirror symmetry is at the level of cohomology, or you mean some homological mirror symmetry behind that?
I'm saying that one prediction of mirror symmetry, if X and Y are mirror, then one prediction of mirror symmetry is that the symplectic, that you should have this isomorphism.
Okay, but your Y has to be smooth. Yeah, it's a prediction of mirror symmetry. Otherwise, I don't know what the tangent complex is.
Sure. Yeah, I suppose I should say, yeah, assuming that Y is smooth, then this that I've written on the right is the correct thing to write, and if Y is not smooth, then we need to replace it with something, which I don't think I have examples.
And this K variety is just K variety, nothing more. Like if X is affine, so Y doesn't have to be affine, I assume. So then we do not have the generation of Hodge to the RAM, so it's indeed sum over PQ of what you have written, not of any DRAM cohomology on the Y side. Yeah.
So yeah, so another prediction of mirror symmetry in this case would be that the S1 equivariant symplectic cohomology would be isomorphic to the de Rham cohomology of Y.
Okay, so this is interesting. So, and equivariant, it should be, can be thought of as a family, so that, I mean, what kind, it's a question, maybe it's a kind of a side to, from your talk, but if Y were a smooth projective kind of imagine, then probably the blue side, there would be the degeneration of Hodge to the RAM. So then you can include the right-hand sides of green and blue lines into the family over, at least over the line, the auxiliary parameter, which is Hodge theory. And probably you have this on the left-hand side as well. And this probably is equivariant parameter of this S1.
Precisely, yeah.
Okay, all right.
Yeah, and I mean, maybe it's a good time for me to say that the results. So I've written down this particular prediction of mirror symmetry rather than, for example, this refined version, the S1 equivariant version, or other predictions of mirror symmetry, such as homological mirror symmetry, because that's what we proved our theorem about. But the circle of ideas somehow should also, homological mirror symmetry should fit in with the ideas I'm going to talk about. Similarly, this S1 equivariant version, it's just that we focused on these particular invariants because it's kind of, some, as you'll see, some non-straightforward things show up, and so we just wanted to understand them in this simplest case. Okay, so yeah, you should think of this as just one prediction of mirror symmetry, which we're trying to understand an aspect of in this case.
Can I try to understand? The SH is a symplectic cohomology of X. X is a symplectic manifold.
Yes, X is one of these Liouville domains.
Okay.
Maybe I should have this SH of X here. is
And the K actually is the
cohomology
coefficient that's for quantum cohomology case, that's the rational field of rational functions with Q as a variable. Am I correct?
So in this case, we have
on the right-hand side of the variety Y is different.
So here, so there are two coefficient rings in my talk. There's little k, which is an arbitrary commutative ring, and there's big K, which has an extra parameter Q. It's formal Laurent series in Q with coefficients in this little k. So,
Okay.
and quantum cohomology has the big coefficient field. Symplectic cohomology has the small one.
Okay, thank you.
Okay, because the spoiler is that this capital Q is going to be the deformation parameter in my title. I'm going to show that quantum cohomology is obtained from symplectic cohomology by, passing to the, adjoining this variable Q and then deforming, the differential with some higher order terms in Q. Okay, so as an example of this version of mirror symmetry that I've said here, C star is mirror to itself. So its symplectic cohomology of C star should be isomorphic to this tangential cohomology of C star. So what does symplectic cohomology of C star look like? Well, here's a picture of C star. It looks like a cylinder. And there are some constant orbits which contribute 2 generators. There's an S1 worth of constant orbits, and the cohomology of S1 has rank 2. Then on this end, you have orbits which wrap once around that end. There's an S1 family of those orbits. So again, they contribute 2 generators. Then S1 family of orbits that wrap twice around. They give you 2 generators. And similarly on the other end, you've got orbits wrapping once around, twice around, and so on. And when you put it all together, you've got a Z worth of generators on the top line, and they give you the basis of Laurent polynomials in Z. And then you've also got a Z worth of generators on the bottom line, and they give you, again, Laurent polynomials in Z, but you think of those as multiplying the tangent vector del del Z. And together you get this whole tangential cohomology of C star. And of course, I've only written isomorphic. I haven't said isomorphic as what. There are various algebraic structures that are respected. For example, it's a Gerstenhaber algebra. It's a more precisely, it's a Batalin-Vilkovisky algebra, isomorphism, etc. But for the purposes of the talk, the main focus will just be on seeing these things as vector spaces. And not
so in this C star example case, that the little k coefficient is complex numbers.
Yeah, you're right. I really should have, I should have specified. I mean, really, I should have said that this C star. I should have said K star here.
And that's the GM over K.
Yeah, exactly, GM. Yeah, so SH of X, with these K coefficients up here. So that, I mean, this coefficient ring with respect to which you take symplectic cohomology should match the K, the coefficient, the base ring of Y. Okay. So now let me introduce the geometric setup, which I'm going to use. So M is going to be one of these compact monotone symplectic manifolds. D is going to be what's called a simple crossing symplectic divisor in M, which roughly, I mean, so the components Di should be real codimension to submanifolds of M. They should be symplectic submanifolds, and there is also some compatibility of orientations condition along their transverse intersections. That's what this simple crossings condition, so the appropriate symplectic version of the simple crossings condition means. And this, we recall, M is monotone, means the first Chern class of the tangent bundle equals the cohomology class of the symplectic form. And that should be some combination of the Poincare duals of the components Di of the divisor with positive rational coefficients. We let X, this is going to be our Liouville manifold. X is going to be the complement of D in M. And this means that we can choose a primitive theta for the restriction of omega to X. So that means this holds. And this turns X into a Liouville manifold. And we can sort of place a restriction that the cohomology class in relative cohomology of M relative to X is given by this corresponding combination of Poincare dual classes of Di. Okay, so the most interesting examples are the ones coming from algebraic geometry. So we can take M to be a smooth Fano variety, omega to be the curvature of the anti-canonical bundle, D to be a simple normal crossings divisor, which is the vanishing locus of some section of a power of the anti-canonical bundle, which vanishes to order proportional to lambda I along component Di of the divisor. So this ensures that X is an affine variety, and this divisor, sum of lambda I Di, is anti-canonical. Okay.
So log Calabi-Yau is not in the class, or what?
Yes, X can be log Calabi-Yau if so we have this C1 equals, well,
Where is C1? Ah,
so,
C1 on the left, yeah.
yeah. So if so this is actually going to be a key part of the talk that will come up later, but yeah, if lambda I is 1 for all I, this is the log Calabi-Yau case. Okay. Now, the conjecture that we're interested in, and we'll try to prove, is that under appropriate hypotheses, the quantum cohomology of M is the Fleur cochain complex, which computes quantum cohomology of M, is a deformation of the symplectic cochain complex of X. And there is a resulting spectral sequence whose E1 page is given by the symplectic cohomology, and it converges to the quantum cohomology of M.
Is there any geometric meaning of the Maurer-Cartan element?
Yes, I mean, so in the result that we prove, deformation is just in the sense of deformation of cochain complexes, but we strongly expect, and I mean, maybe I'll say more about the L infinity version of this, and indeed you can give a geometric interpretation of this Maurer-Cartan element. But that part is not rigorously proved. Okay, but just even to think about this as a statement about sort of just cochain complexes of vector spaces, you already need hypotheses to impose hypotheses, or it's just not going to be true, as the case that M is projective space and D is a hyperplane shows. Because in that case, the symplectic cohomology of X vanishes, and you can't have a spectral sequence from whose E1 page is 0 converging to the quantum cohomology of projective space, which is non-zero. This can't happen.
Sorry to interrupt, Nick. What was the what is this K? I didn't hear what you said that was. This factor in this in E1 page.
What is the what?
You've got symplectic cohomology tensor something. I can't. What's
is the associated graded of this coefficient field,
okay,
capital K. I mean, the point is that you're going to adjoin this bigger, you're going to tensor with this bigger field K, and then you're going to capital K, and then you're going to have a differential, you're going to look at the Q-adic filtration on there. And this is sort of the filtered complex which is going to give rise to this spectral sequence.
I see.
But
okay.
the E1 page is going to be the associated graded of that, which means you have to take the associated graded of this coefficient ring.
Thanks.
Okay, so as as motivation from mirror symmetry in the log Calabi-Yau case, which Jan already referred to. So in that case, mirror symmetry for X. So we expect that X is going to be mirror symmetry to some variety Y, and M is going to be mirror to the same variety Y, base change to capital K, and put a potential W on it. So mirror symmetry for the top line, that's this mirror symmetry here, gives this prediction, which I already wrote down, and mirror symmetry for the bottom line gives this prediction, which I wrote down earlier. And our conjecture says that there's a spectral sequence here, this one here. This is our conjecture. And on the other hand, that fits in with the hypercohomology spectral sequence. So there are two of those, and it's the one that's usually labeled Roman capital 2. which has E1 page, this tangential cohomology of Y, and converges to the hypercohomology of this complex, which, you know, it has all the same sheaves in it, but the differentials get replaced by, instead of 0, they're given by contraction with dw. So you turn on a differential. So you can see how this is a deformation of the complex on the top. And this is, by definition, the ring of functions on the derived singular locus of Y. Okay, so let me finally state our theorems. So the first theorem says that there exists a filtered complex, which is whose associated graded is quasi-isomorphic to the symplectic cochain complex tensor with the associated graded of this coefficient ring K adjoin capital Q, although actually you need to sort of take a slightly larger, you actually need to take K adjoin Q to the A, where A is a generator of the subgroup of Q spanned by these lambda I. And such that this filtered complex, if you just regard it as an ordinary complex, then it's quasi-isomorphic to the Hamiltonian the Floer cochain complex of M. So this gives you a filtered complex computing quantum cohomology of M, and whose associated graded is quasi-isomorphic to symplectic cohomology. So in particular, you have some spectral sequence whose E1 page is given by what we want, this symplectic cohomology of X, but it need not converge. So you need an extra hypothesis to make this spectral sequence converge to the cohomology of this filtered complex. And that hypothesis is that lambda I is at most 1 for all I, these weights in our anti-canonical divisor supported on D. So this is very similar to, or very closely related to the notion of log Kodaira dimension. So roughly speaking, this affine variety X is of log general type if lambda I is strictly less than 1 for all I. And it is log Calabi-Yau if lambda I equals 1 for all I. And it's roughly log Fano if lambda I is bigger than 1 for all I. So our hypothesis B is saying it's one of these first two situations. So M should be Fano. In fact, Calabi-Yau is also okay, although that's the work of other people, which I'll mention. And X should be log general type or log Calabi-Yau, roughly. And our theorem says that under this additional hypothesis, the spectral sequence associated to the produced by theorem A converges to its cohomology, which is to the cohomology of the filtered complex, which is quantum cohomology of M. So this is what we hoped for. And as promised, a very similar result, and virtually the same result, is proved in the case that M is Calabi-Yau by MacLean and Sun, Yuhan Sun. It's a bit different. You don't need a hypothesis B in that case. So it's just M is Calabi-Yau and no hypothesis on these weights lambda I. Okay, so that's theorem. That's our theorem, sort of establishing appropriate hypotheses for the conjecture to hold. And a further result is that under this same hypothesis. The skeleton of X, which I described before, is what's called SH full, which is a property that roughly means it sees all of the interesting Floer theory in M. So it's non-displaceable in M, non-displaceable by Hamiltonian isotopies. It intersects any Floer theoretically non-trivial Lagrangian. And again, analogues of this have been proved by Tonkinov and Varolgunes in the case of the Demis-Calabi-Yau, but they didn't need this hypothesis.
Does it mean that it has only one X group as an object to the Fukaya category?
Sorry, what do you mean one X group?
I mean that the higher X vanish or something like that. I mean this rigidity condition, I'm just trying to make sense of it because it's skeleton. I mean, I'm trying to think about that as kind of categorical statement, and where roughly there is a generator on one side and on the other one, and the skeleton, I would like to see it as a generator for the Fukaya category. So that's I'm just trying to.
Yeah, I mean, the skeleton need not even be smooth. So
yes, but it's kind of, let's pretend. Yeah, if I'm, you see, it doesn't have to be smooth, but I can still think about X groups in terms of, I don't know, like perverse sheaves, that story of, you know, GPS.
Yeah, roughly speaking, I mean that this is a statement in M. So roughly speaking, it's saying that all of the Fukaya category of M can be represented by objects living on the skeleton S.
Yeah, that's what I mean, that when I said that it's sort of generator.
Yeah.
Of the Fukaya category.
Right. Whereas when this hypothesis is not satisfied, you can have objects of the Fukaya category of M which are disjoint from this skeleton. They just live somewhere else. But X groups, I mean, you can have, for example, the skeleton can in some cases be smooth. It can be, for example, a sphere, and its X group, it can, so it's cohomology, Floer cohomology can be the cohomology of a sphere, which is
Yeah. So yes, so I'm wrong in that sense, but kind of the Fukaya category probably is a category of DG modules, or the home from the skeleton to itself, probably properly understood. Still kind of makes the Floer theory, converts it into some algebra. You see, every Lagrangian intersects, so then which gives you the functor to the category of modules, or this X algebra from the skeleton to itself. And it's non-displaceable, which probably kind of means that it's some kind of rigid. Yeah, it looks as it is a generator in some sense. I don't know in which one.
Yes. Yeah, I mean it's yeah, it is somehow saying that yeah, that the Fukaya category of M is entirely visible on the skeleton, and so somehow, in order to understand the Fukaya category of M, it is sufficient to understand somehow the Fukaya category of a small neighborhood of this skeleton together with this Morakatan element telling you how it gets deformed.
Yeah, that's exactly. I think that's kind of sort of our approach with Maxim to Fukaya categories with singular Lagrangians, which probably is related to your kind of work with Borman. Yeah. So you have some kind of Liouville or whatever, maybe Weinstein, a neighborhood of the skeleton, and inside of it, the Fukaya category is kind of something which essentially lives over integer. I mean, it's something very simple, and you should add the Maurer-Cartan element in order to handle Lagrangians from outside of this neighborhood. Yeah. Okay, great. Thank you. Mm-hmm.
Yeah. There's certainly. Yeah, well, we are trying to realize a picture as you describe. Yeah, but yeah, I should caution that. I mean, we don't yet do all of the technical details, and yeah, part of what we're trying to understand here is the limitations when this hypothesis B is not satisfied. Okay, so here are some examples to show you these hypotheses in action. This hypothesis in action. So you can take M to be the two-sphere, D to be a set of n points. So then the sum of these weights needs to be equal to the area of the two-sphere, which is 2, by the monotonicity condition. And the skeleton divides the two-sphere up into n regions, each containing 1 point pi and having area lambda I. And this skeleton is displaceable if and only if hypothesis B is, hypothesis B is satisfied, which means lambda I is at most 1 for all I. Because if you had one that was if lambda I was bigger than 1, then you'd have one of these regions that occupied more than half of the total area of the sphere. So you could somehow rotate the sphere so that everything else mapped entirely inside that region, and S became displaced from itself. As another example, you can take M to be a Tharno-toric variety. Then the weights lambda determine where the skeleton lies. The skeleton, you can arrange that the skeleton is going to be a torus fiber, and this hypothesis, well, the hypothesis B is satisfied if and only if all the weights are 1, which is true if and only if this skeleton is equal to the central monotone for torus fiber, which is known to be the only, interesting one Floer theoretically. For example, it's known to be the only non-displaceable fiber when the toric variety has dimension at least 3 by work of McDuff. And you can also see in this case where M is CPN and you remove some number of hyperplanes, hypothesis B means the number of hyperplanes has to be at most n, which is true if and only if this symplectic cohomology, sorry, I should have said, sorry, got things the wrong way around. Hypothesis B is true if and only if K is strictly greater than n, which is true if and only if symplectic cohomology of X is non-zero. Because when K is less than or equal to n, then X decomposes as a product of a non-trivial affine space with something, and symplectic cohomology of the affine space is well known to vanish. So you can't have this spectral sequence result. Maybe I think what time should I finish?
No, you shouldn't.
I shouldn't.
Yeah,
No.
yeah. You can go all the time if you wish.
Okay, I won't go very much over time.
Okay.
So the idea of the proof is that we should consider Floer cohomology of M computed using a Hamiltonian, which has sort of gets bigger and bigger as it goes toward, a family of Hamiltonians HI, where HI gets bigger and bigger along the divisor D. So just to remind you, the skeleton lies at rho equals 0, the divisor lies at rho equals 1. And we look at these family of Hamiltonians which sort of look like this. They have slope I. Roughly they look like the function h of rho equals I times rho, but smoothed a bit. So then the Floer cohomology of M doesn't depend on the function you use to define it, the Hamiltonian you use to define it. So this first equality here is sort of a trivial consequence of that. You're just taking a direct limit over a bunch of complexes which all compute the same cohomology. And sort of by construction, the orbits of these functions HI break up into sort of orbits that lie inside X, which is these ones, and orbits that lie on D. And by playing some games with gradings, you can sort of cancel out this bit of the complex. You can sort of take a sort of quotient by a cyclic subcomplex, although it ends up being a subquotient that you need to take, but okay, it's fine. And then you end up just with this bit of the complex left over here, which precisely computes, comes from orbits of Hamiltonians inside X. And the only thing is that the differential counts Floer trajectories which are allowed to pass through the divisor. So you can expand it in powers of Q, where the Q to the J term counts trajectories passing J times through D. So in particular, the leading order part, del 0, counts trajectories which don't intersect D. And in particular, this gives you precisely the differential for the symplectic cochain complex of X. So this is already enough for us to prove the theorem A, which said that we have a filtered complex computing quantum cohomology of M and whose associated graded gives you symplectic cohomology of X. And to prove this convergence of the spectral sequence result, we need to compute the gradings of the orbits which wrap around the divisor. And they turn out to be proportional to this 1 minus lambda I. So under our hypothesis B, I'm sorry, I changed hypothesis A and hypothesis B at the last moment and didn't get them all. So under this hypothesis B, you can show that this filtered complex is bounded below, which is the condition you need to ensure that your spectral sequence converges to its cohomology. Okay, so I'm skipping over that. All right, so I had an example prepared in the very simplest case to kind of show you what goes wrong, sort of how theorems A and C apply in this very simple case, but I don't know, maybe I can come back to that if anyone wants me to, because I just want to mention these conjectures, which are sort of about strengthenings of the result. So the first conjecture is that the deformation which we've described is in fact controlled by a Morikawa element for the natural L-infinity structure on the symplectic cochain complex of X. And this is the result which Borman and I announced originally, and it's clearly more useful than more precise and more stronger than what we've ended up proving. But yeah, so somehow the point of what we did so far was to sort of elucidate the role of this hypothesis B in the result. B is another one. So in the log Calabi-Yau case, this would have the consequence that once you know mirror symmetry for X, this affine variety, then you know that quantum cohomology of M is obtained by deforming by this beta M. So that implies that the quantum cohomology is isomorphic to the tangential cohomology of Y deformed by a Morikawa element. And it turns out that for grading reasons, that Morikawa element can only be a function on Y. It can't be any more complicated polyvector field. And when it's just a function, then by definition, pretty much, this deformed tangential cohomology is precisely the ring of functions on the derived singular locus. So it sort of says that, you know, once you know mirror symmetry for X and, you know, for X, you're sort of automatically given a function W on the mirror such that you have mirror symmetry, which satisfies mirror symmetry for M. And there are versions, similar statements for homological mirror symmetry as well. sort of automatically upgrading homological mirror symmetry for X to homological mirror symmetry for M. Another strengthening of this result is a conjecture which is based on suggestions of Pomigliano and Seidel, which is about what happens if this hypothesis B is not satisfied. The conjecture, for which there's some sort of reasonable evidence, is that there's still a spectral sequence arising from our theorem A. The only thing is that it need not converge to the quantum cohomology of M. And the conjecture is that instead it converges to a certain subspace of the quantum cohomology of M, which is precisely the intersection over all components of the divisor which violate this hypothesis B of the zero generalized eigenspace of quantum cut product with the Poincare dual of that DI. So for example, if D is smooth, then this would just be the zero generalized eigenspace of quantum cut product with C1, which has plays a well-known role in mirror symmetry. So for example, you can take M to be CP1 cross CP1, D to be a degree 1,1 hypersurface. So then you can arrange that the skeleton is the two-sphere, anti-diagonal two-sphere. And in this case, Eliashberg and Polterovich in 2010 constructed a spectral sequence exactly as in this conjecture. Its E1 page is the symplectic cohomology of the two-sphere, and it converges to the zero generalized eigenspace of quantum cut product with C1 on quantum cohomology of M. So this was part of the motivation for this conjecture, but of course the conjecture is much more general. Yeah, it's also interesting to compare this with results of Ritter and Venkatesh about symplectic cohomology of total space of a negative line bundle. Their result says that Ritter's result says the symplectic cohomology of X is the quotient of the quantum cohomology of the base of the line bundle by the zero generalized eigenspace. So it's somehow complementary to this conjecture of ours, which says, something about the symplectic cohomology somehow only seeing the zero generalized eigenspace rather than the others. Okay, so I think I should probably stop there and ask the questions.
Yeah, thank you very much. As for this conjecture about Maurer-Cartan, on the symplectic side, I mean, can you describe it as counting of, I don't know, some stable maps with additional structures? Because on the mirror symmetry side, yeah, it looks kind of easy, but
yes, so what you can so beta M can be expanded like this, and the gamma 1 is has a natural geometric interpretation. Basically, if your divisor looks like this, then gamma 1 is just the simplest orbit that just goes once around the divisor. And in the log Calabi-Yau case, for example, there actually aren't any, almost never any terms beyond gamma 1. In fact, the only terms beyond gamma 1 have to be multiples of the identity, and these showed up in Giventhal's proof of mirror symmetry for Fano complete intersections as some sort of special shift that shows up for Fano index 1 complete intersections. But so that there's somehow modulo this sort of very special thing that can happen. In the log Calabi-Yau case, you can really pin down what this Morikatan element can look like. In general, there can be these higher order terms which are not as explicit, but you have a, but you know, well, we haven't written it, but you know, we have an outline of an argument that would sort of show abstractly that this thing exists, but it somehow passes through some homological perturbation lemma, and so it's not completely explicit.
Okay, right. More questions?
I had a question. So I was hoping maybe you might just for a moment, like explain the homological mirror symmetry, the categorical version, and just sort of see these as, I guess, Hochschild cohomology or some kind of thing of this type. And in particular, I wanted to ask, you know, if you could do that, if you could then maybe this last conjecture, you know, that you mentioned, sort of say what are the categories in this setting, maybe where you're not satisfying hypothesis B, for example, is there a kind of a categorical version of that? Like, what's the picture there?
Let me first answer the first question. So there's a further enhancement of this L infinity enhancement of the conjecture, which says that the L infinity version of the closed open map sends beta M to the natural deformation of Fukaya category of X. So I'm writing Fukaya of X because I mean like compact exact Lagrangians in X. So there's a natural deformation of that category given by just counting holomorphic disks that pass through the divisor. And so there's this, part of the way we do our, construction that hasn't been written up yet is so that this will also hold, that the Morikatan element we construct gets pushed forward under the closed open map to that natural Morikatan element describing that deformation. so in particular, you know, if in this picture, you know, if you've got Fukaya categories here instead of, if you've got Fukaya category of X and Fukaya category of M, it's saying that the Fukaya category of M is sort of is a deformation of Fukaya of X given by this particular Morakatan element, which corresponds under this picture to this function W, and then so you should have some statement about, you know, matrix factorizations of W being a deformation of the category of coherent sheaves of Y. So you know, you need to make sense of these statements and check that there are enough objects and all the rest of it. But it's kind of saying that there's just this one Morakatan element beta M, which describes this deformation process on the symplectic side. So then if you take the corresponding Morakatan element, which is just this function W on the mirror, then you get the corresponding deformation. So as long as there are enough objects to generate the category, you're okay. And then about this conjecture, so somehow I mean, one thing I can say is one thing I can say, which is kind of, I mean, I don't understand as well, but it's kind of suggested by Venkatesh's work, Sarah Venkatesh's work. So you sort of got this, so there's this picture of the skeleton, the divisor, and I didn't state this version of our results, but you know, under hypothesis B, we show that this skeleton sees the whole Fukaya category. Because it is this, it's SH full in Umut, Varolgunes terminology. So we actually proved a version of that result in the case that hypothesis B is not satisfied, which said that there's some kind of specific neighborhood of the skeleton which is SH full. And if hypothesis B is satisfied, then that neighborhood can be arbitrarily small. If it's not satisfied, then it has to have some certain finite size. So, you know, what you would expect, I guess, is that sort of the, I mean, we know that the Fukaya category sort of splits up into these components indexed by eigenvalues of C1. And roughly speaking, it kind of suggests that the Fuk0 lives on the skeleton, but the other components of the Fukaya category, you know, may be generated by some other Lagrangians. And we need to make this neighborhood that appears in the version of our theorem, the refinement of our theorem that I didn't state. You know, that neighborhood has to be big enough to see these other Lagrangians. But we have some kind of quantitative version of how big the neighborhood has to be for this SH fullness to appear. And Venkatesh's result actually kind of says that it's a more precise quantitative version of this Ritter result, which says that, so there's this relative symplectic cohomology, which I didn't introduce, but she kind of shows that the relative symplectic cohomology of a neighborhood of the zero section in this negative line bundle kind of sees more and more of the sees more and more of the eigenspaces of quantum cohomology as you increase the radius of this neighborhood. So it's kind of, there's some analogous picture here, but to make it more precise, I would need to use this relative symplectic cohomology introduced by Varolgunes, which I didn't mention at all in my talk. Well, I mean, I may be doing Umut a bit of a disservice by doing that, but that's the version of the talk I thought was maybe would work best today. But yeah, so somehow there should be some kind of quantitative version where you sort of, as you increase the size of this this neighborhood, you can kind of say more precisely how many eigenspaces, sort of components of the Fukaya category you can see as you increase this size.
That's great. One other small, like minor question I had was just sort of, so these, is there some sort of more general, like a Novikov kind of case where, so if you have components of your divisor where you deform per component kind of, is there some result along those lines, or is it just sort of orthogonal to what you're doing? Or?
No, you can do a refinement like that. Yeah, you could replace this coefficient. Yeah, I mean, so we use this coefficient ring field throughout. We could also have used
right,
where we
sort
could
of
have
deforming over the sort of the Kähler moduli in a sense, rather than just
yes, precisely. Okay. We could have deformed over the Kähler moduli. Some of the sort of our algebra is a little more complicated, but I mean, yeah, it shouldn't be a problem. We didn't, because we were proving results for this relative symplectic cohomology, which Varolgunes defined, and he did everything in his thesis sort of in this single variable Novikov field version. We didn't go through and sort of check all of the slight changes that are needed to it. Yeah, it shouldn't be a problem to do a version like that.
Thank you. Great talk.
Thank you.
Okay, more questions? Last chance. All right, if there are no more questions, Nick, thank you very much for your talk. I understand that there is a paper in archive,
Yes.
so people can look for the details. All right, thank you, and this is it for today.